Hi, everyone, and welcome to the final episode, the season finale of
The Earth is Flat on Planet Pluto,
an online live cosmic talk show about astronomy, science, and other stuff where the guests are the clear highlight and where you can ask any questions and also participate by using the chat on this side. Now, every Wednesday at 5:30 p.m. UK time, we have been bringing you a cosmic topic and amazing guests who share their passion for science and space. This is already the 8th and final episode, but just like in all others, things can and will definitely go wrong. I must stress that this is core to the scientific method. Because when things work perfectly, we never really learn anything at all. During June and July, I've been your host as we attempted to bring you lots of astronomy, science experiences, the human side of looking up, and also a lot of fully random but hopefully fun stuff. My name is David Sobral, and I am an astronomer and a scientist. Just like everyone else on this amazing yet insignificant planet, I'm 10% made of cosmos and 90% made of stars, which formed billions of years ago. Everything started with the first generation of stars made of hydrogen and helium, the pioneers that lived fast and died young, and that by exploding as supernova, you get the concept, created and released the first heavy elements that astronomers call metals, and that gets people in chemistry confused as hell whenever we talk to them. Before the first stars, there was only physics and astrophysics. After the first stars, everything else became possible, including, for example, samba. The first generation of stars created and released the first atoms of carbon, calcium, and iron, and almost all others, some of which are actually part of us right now. You should thank the first generation stars also for being alive. Now, by using the largest telescopes in the world as time machines, we can now see further than ever, billions and billions of years back in time, each time getting closer and closer to the epoch where chemistry was made possible. When the first stars made of just hydrogen and helium created and released the first heavy elements. In a quest to find bright, super distant galaxies that were thought to just not be there at all, and therefore searching for them was surely a waste of time, a little over 5 years ago, we found and confirmed the first two of such galaxies. One in particular was incredibly surprising, not only because it was the brightest of those galaxies ever found, but also because it lacked any signatures of heavy elements, and it could be powered by some first generation stars or even a special kind of supermassive black holes. We named it Cosmos Redshift 7 or CR7. It was discovered by me, Jorrit Matthey, and Sergio Santos, both here with us today. Even though it is currently almost 30 billion light years away from us, the fact that it is so bright made it possible for us to measure its distance and confirm it with just 15 minutes of raw data using the 10-meter Keck telescope in Hawaii. But how did we discover this galaxy? Why did we call it CR7? Is CR7 playing alone in the universe, or is there a team of super bright galaxies? Is there a connection between the galaxy and the football player Ronaldo? What have we learned so far about CR7 and other bright distant galaxies that we have been discovering and studying over the last 5 years? How hard is it to find these galaxies, and can you do it at home with your computer? Our amazing guests discover and study galaxies across a range of cosmic times and will share how exciting it can be, along with answering any questions on the live YouTube chat that you can use right here. And the voice from beyond will put them to our guests. As this is the final episode, and because it is about CR7 and other bright, super distant galaxies, you may even ask me questions if you like. So it's definitely going to be extra galactic. For now, though, please welcome our amazing guests for today. Jorrit Matthey, that's joining us from ETH in Zurich, Sergio Santos from Lancaster, and also Eda Wade, also joining us from Lancaster University. Now, thank you so much for coming into the show. I hope you're all doing very well. And I would start with Jorrit. Actually, I see you're in La Palma. It's a very nice site. You're ready for the sunset. And for those of you that don't know about Jorrit, so you did your BSc degree at Utrecht, working on globular clusters. Apparently, the department no longer exists. So that's an interesting story. Then you moved to do your master's degree at Leiden, where you got a cum laude distinction. And then you won a Huygens Fellowship to conduct your own research project at Leiden for your PhD, where you were trying to identify the origin of galaxy formation with both observations and theoretical models. In the process, apparently you wrote an incredibly heavy PhD thesis, and you authored 11 first author papers. And one of those has already been cited over 150 times. Your work led to the discovery of some of the brightest distant galaxies, and it has now been recognized multiple times internationally with the award of an incredibly prestigious 5 years Wiki Fellowship at ETH. So it's basically like a Hubble Fellowship, but better, making you an even more independent researcher. And then this was followed by national and international prizes. So you got the 2018 prize for best PhD thesis in Leiden, and then the prize for best thesis from the International Astronomical Union in 2019 in Galaxies and Cosmology. And you recently received the Merrick Prize for best observational astrophysics thesis that comes with 20,000 euros. So first of all, thanks so much for being on the show, and congratulations for your amazing and brilliant work. And to start with, could you tell us a little bit more about why we search for and study distant galaxies?
All right, thank you. It's very nice to be on the show. I must say I've been following the number of views on the show, and they're increasing rapidly. So I hope they're not quenching as soon as people are seeing me. So for me, the motivation of why it's interesting to look at distant galaxies, galaxies in the early universe, is to learn about our own cosmic origins. So as people may know, our solar system is part of a larger structure of stars and gas called the Milky Way. And the Milky Way is a galaxy. So we're part of this very fundamental structure of galaxies. And it's interesting if we want to understand how our own Earth, our own sun, and how we eventually formed, it's important to understand how galaxies form. Unfortunately, galaxies evolve on a very long time scale. During the entire history of humankind, the Milky Way didn't change at all. So if we want to understand how the Milky Way looked in the past, we have to look at other galaxies. And we can actually do that by looking very far away from us using large telescopes. We can look in the past because the speed of light is not, well, it has a limit, it has a speed. So that means that if we look at distant objects, we actually look back in time. And if we want to understand how our own Milky Way formed, and if we want to understand that empirically, so it motivated by observations, we have to look at these distant galaxies to answer that.
And so basically you use telescopes as time machines. That's pretty cool. And are these distant galaxies anything like our own galaxy, the Milky Way? Can we see like spiral structures and well-defined structures?
Well, there is a large variety in distant galaxies. There's also a large variety in terms of how far back we can travel in time. We can basically slice our way. Sergio will, I think, explain that very beautifully later on. We can actually slice our way back into time, just like archaeologists digging deeper and deeper to see how our galaxies looked like earlier in the history of the universe. And we know that, well, even if we sort of, the universe is now roughly 14 billion years old, but even if we look back already 10 billion years old, if we look this movie is too distracting, David. But basically, there are spiral galaxies like our own Milky Way already relatively soon after the Big Bang. There was a paper a few months ago, or a few weeks ago even, discovering a very large, massive rotating galaxy, almost by accident, that rotates just as our Milky Way does. But other galaxies actually look very, very different. Instead of being a nicely flat, structured disk and with spiral arms, they are more like a collection of clumps, as we will discuss later.
And in your research, essentially, how far back in time do you typically go in your day-to-day job?
My day-to-day job, so currently I'm working on observation of galaxies that are seen as they were 11 billion years ago. So when the universe was roughly 2 billion years old. And this is actually, we call this middle redshift. This is not even extreme. It's quite simple. You can even find those galaxies with telescopes like that one. But I've also looked at galaxies, in particular the CR7 galaxy, which is observed really in just a few 100 million years after the Big Bang, roughly 600 million years. This is not the first light that we in theory can see, but we're getting quite close.
And I mean, so when we talk about distant galaxies, how exactly can we measure distances to such far away objects? I mean, surely we can't just stretch a ruler, right, and then bring it back. How do we know that they're that far away?
Yeah, so actually for most galaxies, we don't even measure, we actually almost never measure, we never measure distance. For some objects, for some galaxies, we can measure distance in a very accurate way because we have a standard candle, for example, the type of supernova explosion or a pulsating star. So we actually know how bright it should be and we know how bright we see it. And from the difference, we can infer the distance. But for a galaxy, like a typical galaxy in the early universe, we cannot do that. And we can only measure redshift, which is a measure for distance. And redshift is, as the universe expands, light is stretched, the wave length of light becomes longer, shifting light to the red. And we can actually measure this redshift if we see an emission line at a certain wavelength. And if we know which emission line, which wavelength it should be, we can measure what redshift it is. In this movie, you can see this Lyman alpha emission line that we often use. And the more distant we go, so the more to the right that galaxy goes, this emission line is shifted to the red. So now it's at 5,000, which our eyes see as green light, but now it shifts into the red and even infrared at some point. So by measuring the wavelength, we measure the redshift, and from that we infer a distance. So it's never a direct measurement, and this measurement is also dependent on our understanding of the universe, whether there is dark energy or not, and those kind of things. It's a bit complicated.
So the exact distance is very hard to measure, but with Cosmos redshift 7 being at a redshift of around 7, for people that are wondering, how much is this in kilometers?
So I think this is, well, kilometers is not really a useful unit. I mean, I'm also not saying my length in angstroms because it's not very useful. It's even worse, actually. So the distance to CR7 is 100,000 billion kilometers. Quite a lot. It's very hard to imagine. It's a 1 with 24 zeros.
So for people at home wanting to write the distance in kilometers to CR7. So what kind of distances do we typically use then? That are more appropriate to measure such large ones?
So, well, we use redshift, but if we transform redshift into a physical unit, we use megaparsec or parsec. Parsec is a typical astronomical unit because it's based on some Earth-centered observable, how much stars shift when the Earth comes from winter to summer. And 1 parsec is roughly 3 light years. 3.6 light years, if I remember correctly. So we typically use megaparsecs, and I think in that unit, CR7 is about 6,000 megaparsecs away.
A lot megaparsecs away, definitely. And so the other thing that people might want to know is, how do you discover galaxies? Is it just like you go to La Palma, I mean, you're not in La Palma right now, but do you just go there, you point a telescope up, and that's it? Because, I mean, there's almost 2 trillion galaxies in the universe, right? So surely by just pointing at any random location, you will find galaxies, right?
Yes, I think if you go to a telescope with a large enough mirror, for example, 2 meters or bigger, and if you point it to a purely random part of the sky and avoid the Milky Way, then you probably will see galaxies that haven't been seen before, or at least not by a human. But the question is, of course, how do you discover interesting galaxies, or kind of galaxies that you want to discover, I guess.
So specifically for like very bright and distant galaxies like CR7, what's the secret to finding them?
So the secret is, well, it's a bit, sounds a bit weird, but very distant galaxies are very faint. So you actually are better off looking at a very small part of the sky for a very long time. So you can see the very faintest sources of light, which are more likely to be very distant. And this is what people have been doing very successfully for decades, or 2 decades, and with telescopes like the Hubble Space Telescope. But when we started 5 years ago, or even 6 years ago, we actually tried to do this in a different way by looking for a compromise, by going still very deep, and taking very sensitive observations, but simultaneously looking at much larger areas of the sky that should contain more rare and luminous systems. The real difficulty is then to make sure that the objects you're seeing are actually these distant galaxies and not something else, because there's a lot of stuff in between. There are stars in our own Milky Way, and there are supernova explosions that can mimic how galaxies look like. And there are also galaxies that are not that far away as you would like to see them. So the challenge is really to make sure that you're not seeing those objects.
And we'll definitely come back to that. And first, I'd like to introduce one of our other guests, Sergio Santos, who was also our guest in the Portuguese edition, for those of you that follow that as well. So for those of you that don't know Sergio, so he did his bachelor's at the University of Lisbon. And in his 3rd year astrophysics project, he started to hunt for bright, distant galaxies. And he actually found a few candidates, including a few bad-looking pixels that ended up being CR7. Sergio, you then did your master's degree and thesis at the University of Lisbon, and you published your first author paper actually before starting your PhD. And that paper is also quite well cited. It's been cited more than 77 times, which is quite of an achievement for a master's student. Now, you just finished your PhD at Lancaster, and you have your Viva apparently in exactly a week from now. So best of luck for that. And I guess in a week, you might become a doctor. Not a real one, but a doctor in astrophysics. So in your research, you've been discovering and studying galaxies by essentially traveling back in time between 11 and 13 billion years. And you have been studying a unique sample of 4,000 distant galaxies, many of them progenitors of galaxies like our own Milky Way. In your PhD, you have been looking at photons, these light particles that are also waves, with a very specific energy, frequency, and wavelength. And you use them essentially to travel back in time. Those photons are essentially produced in excited hydrogen atoms, and people call them Lyman alpha photons. But can you tell us in simple terms kind of how they are produced and what the hell are Lyman alpha photons?
Yes, so first of all, thank you very much for the invite and the opportunity. And so Lyman alpha emission is an emission line from the hydrogen atom. So what happens is when an hydrogen atom has an electron at an ionized state, at an excited state, it will tend to transition to lower energy state, to the ground state. And when it does these transitions, it emits at very specific wavelengths. And one of these transitions leads to Lyman alpha emission, Lyman alpha photons. And in astrophysics, this emission typically comes from the so-called H2 regions, which you can see on your screen, which are regions of ionized hydrogen. And these regions are powered by very massive stars, which emit very strong ionizing radiation, which will result in emission lines and such as Lyman alpha.
And are these photons, I mean, the red we're seeing, are these Lyman alpha photons? Can we see them?
Lyman alpha is a very energetic transition. It's in the ultraviolet, so we cannot observe it with our own eyes. It's not invisible. But since we are looking at very distant galaxies, and as Jorit mentioned, if galaxies are very far away, radiation gets stretched and gets shifted to the red. And as we go further back in time, these actually ultraviolet radiation becomes first visible. And for example, in a galaxy like CR7, it's actually in the infrared. And it's what we use to actually detect these galaxies.
So basically you try to hunt for these Lyman alpha photons, but when they're redshifted. So by how much do you typically, and especially for your PhD?
The ones that I look at my PhD are redshifted around the visible. So yeah, the picture on the screen. So because the Lyman alpha at redshift 7 that CR7 is detected is already in the infrared, and the ones that I look are on the visible and getting close to the near infrared. Which corresponds to redshift 226, so a bit closer to us.
And can you tell us a little bit about this kind of 3D map that we're seeing and the sample of 4,000 distant galaxies?
Yes, so we essentially use the exact same technique that we used for CR7. We use a very narrow filter. We take an image of the sky, and then we use a very broad filter, broad in wavelength, and take another image of the sky. And we essentially look for sources that are very strong in the narrow filter, and they are very strong there, likely because they have an emission line there. And the position of the narrow filter will detect Lyman alpha at different redshift. And we use 16 of these narrow filters, like the ones you see on the screen, like multiple ones, and each will detect Lyman alpha emission at different look-back times. And we essentially are able to construct samples of these Lyman alpha emitters at multiple look-back times, which gives us this 3D view of the universe.
And I mean, what kind of things have we found out about these very distant and early galaxies?
So these galaxies, they are emitting very strongly Lyman alpha photons, which means that they are very likely going through periods of intense star formation. And so this means that these galaxies, these Lyman alpha emitters, will typically be very young, low stellar mass galaxies. But we are also finding that these population of Lyman alpha emitters, they actually have a very big diversity, a big range of parameters, and that we can actually see Lyman alpha emitters in very massive galaxies, which we may not expect before.
And you were involved also in kind of reducing at least part of the data that led to the discovery of CR7 and also for these large surveys. So was it challenging to reduce and process these huge amounts of data in multiple locations in the sky, particularly like as an undergraduate student, for people that may be watching us live or in the future, they're undergraduates and might think, oh, this is just impossible to be done. How was it for you?
So I would say challenging, but not in a bad way. So it's like exciting that we're doing like actual science, well, as an undergrad doing actual science and actually looking for very distant galaxies that no one has seen before. So yeah, it was like exciting, like applying all the reduction steps to actually go from the raw images that come straight from the telescope to the very final images which we can use to actually find these sources and determine properties such as their luminosity and different wavelengths, for example.
And specifically, for example, for the way that you were mapping the universe with SC4K, how are these galaxies found? So you said that they should shine brighter in specific filters, but do you just like check one by eye, or is it more fancy than that?
Well, thankfully, it's mostly automated, where we essentially have the images, pixels, which pixel has a value, and we run software that detects where there's excess in pixels, excess influx, because there's a source there, and we look at each of the sources that we detect, and we look for specific properties. In this case, very strong emission in the narrow filter compared to the broad filter, and also color breaks. So they're brighter in the blue and in the redder filters than in the redder filters, which is what we will see at the very end when we do the experiment to find CR7.
And essentially anyone can do it in the way we've placed it. It's also with real data. Before we go to some YouTube questions about your research, Sergio, I'd like to introduce our other guest, Eder Wade. It's joining us from sunny Lancaster on the roof, socially isolating from everyone, obviously. Now, Eder, you got your MPhil from Lancaster University last year, so you actually got to graduate, not like this year, and you were studying galaxies and galaxy clusters. And you started your PhD almost a year ago, after being part of the start of actually XGAL Lancaster to the World, this outreach project that led to the creation of this YouTube channel and the activities that people can do, including finding galaxies or mapping the universe in 3D from their homes. For your PhD, you are working with very wide data obtained with a very large telescope in Chile. So these are 4 8-meter telescopes to try to push back in time even further than CR7 to a redshift of 7.7 or approximately 8. We're astronomers, so we love to round things up. And you're essentially looking for the super bright galaxies into what is known as the epoch of re-ionization. To start with, could you tell us a little bit more about what the hell is the epoch of re-ionization?
Yeah, so hi everyone, thanks for watching. So yeah, re-ionization is this crazy time in the very early universe that we still don't fully understand. So yeah, this is a nice little simulation of it. So basically what happened was all of the neutral hydrogen in the universe transformed into ionized hydrogen. And the best model of this so far is called Patchy Reionization. So we basically think that the very brightest stars and galaxies produce lots of ionizing photons, lots of high energy light, that ionize the hydrogen that surrounds them until it was all ionized. So bubbles grew around these galaxies, and the bubbles grew and merged, and then reionization was complete.
So for us to see something like this, or for us to enter this epoch, how far back in time do we need to look?
Yeah, so we need to look a little bit further than where CR7 is, to beyond redshift 7, to about 7.7 or 8. And yeah, so this is at redshift 7.7. The universe was only 0.66 billion years old. And that sounds like quite a big number, especially if it was like the amount of money I had. But if you compare it to the fact that I'm looking back in time, 12.8 billion years, then we see that this is a time in the universe when it was really, really young. And
essentially, why do we say that reionization was the last major phase transition of the universe? Does it mean that it didn't change since then? Like over 13 billion years, it managed to kind of stay the same?
So, well, it's not stayed exactly the same. So lots and lots of stuff has happened in the universe since, like so many galaxies have formed, galaxy clusters, but nothing has really happened on a full universe scale where the majority of the matter has changed phase or form. So here, in reionization, the hydrogen changed from neutral to ionized. So that's like a major thing happening. But if we compare this to before reionization, there was major phase transitions. So like recombination is the opposite of reionization, where all of the lonely electrons and protons formed the neutral hydrogen in the first place. So yeah, nothing has quite happened on the same scale, basically.
And when we look that far back, can we actually see galaxies? And I mean, roughly for people that have no idea, how many galaxies have people found deep within the epoch of reionization?
So yeah, things do get more complicated with observations into the epoch of reionization, but some have been found. So a few weeks ago, Taylor and Rebecca were talking about their work using the Keck telescope to find redshift 9 or 10 galaxies, and there's been quite a few other confirmations around redshift 8. There's actually a really cool Wikipedia page that has all of the records of distant objects that have been confirmed, and there's even like a history of the record holders. So if you go back to like the early 60s, for example, the highest redshift object that we'd observed was only at redshift 0.5, which is like really low, really pretty low redshift compared to what we can do now. So I thought that was really interesting if anyone wants to check that out.
Yeah, so I guess some people, if they just go back in time, they become incredibly famous and this field becomes much easier. Now at a redshift of about 8, have we found, so you've said that there's a kind of a handful of galaxies that people have confirmed. Is there anything like CR7, like that it's spectacularly bright at a redshift closer to 8?
Well, I don't think so. That's hopefully what my PhD will do. I'll hopefully find a redshift 7.7 candidate that will be similar to CR7.
And are you going to call it CR8, or are you going to be more imaginative than that?
I'm not really sure. It doesn't work quite the same way, does it, with like the Cristiano Ronaldo reference? And I'm not really into football, so maybe I'll find someone else cool to name it after. Who knows? So
imagining that, for example, there's no bright galaxy at this early times. Is that still interesting, or will you just get depressed?
Well, it probably would be quite a shame, but it would still be really interesting to see that we can't, if we can't find observed galaxies, then at this redshift, then it's reionization is stopping the observations, so stopping the light getting to us. So when the light is emitted by the galaxy, it'll scatter off, especially the Lyman alpha photons. They'll scatter off the neutral hydrogen. So they need to be inside the ionized bubbles that are large enough to allow the light to redshift to higher wavelengths, and then we can observe it like that.
Yeah, do you want to add something to that?
Yeah, actually, for the record, I actually agree with Heather. I'm also not into football at all.
Well, I'm not really that much into football either. I think Sergio is the only one that's really into football, but he's like a Benfica fan, which Ronaldo didn't play in. So.
No.
Now, I think before we continue, we have a few questions from YouTube. So we might start with the first one, I think from João Calhau, whether there's any difference between galaxies?
Yes. So João asks, is there any difference between the galaxies at the different redshifts that you have found with SC4K? What does that tell us about the universe?
So I assume this is a question for Sergio.
So thank you, João, for the question. So as I mentioned, the galaxies that we found with SC4K are typically very young, very low mass, very blue, even though there's quite a significant range of parameters. Some that are actually more massive, forming more stars, less stars. But in terms of actually are they evolving, I think it's a very interesting result is that the galaxies that we select as Lyman alpha emitters are typically very similar at all redshifts, and the properties usually stay roughly the same for these Lyman alpha emitters.
I think Amaya has a question also about SC4K and what's next, right?
Yes, I ask, what's the next after SC4K? What's the next step to learn more about the early universe?
Well, I can start, but I think this one is more for Heather because, well, after C4K, which goes to redshift 6, we want to go into higher and higher redshifts, basically expand the same work, and which is what Heather is doing. Maybe she wants to add a bit more.
Yeah, so hopefully I'll add an extra slice of of SC4K at high redshift, and yeah, find some more Lyman alpha emitters at high redshift.
And I guess an important, also an important question related with that is like, why should we care about reionization? I guess why go to even more distant galaxies and not, for example, go wider or go to the more close by galaxies?
Well, there's plenty of other people doing all of those things as well. But like, why don't we want to know? Why do we want to know any astrophysics? Like, it's just so cool. We get to find out about like the very first physics of the universe. So I would say that it's much more interesting than black holes, but that's just my opinion.
Is it because it's a puzzle as well? Even if
yeah, there's so much to figure out. Like, even observations in that everything just gets more complicated and more interesting, in my opinion.
So yeah, go ahead.
So I mean, besides like finding galaxies in the epoch of reionization, I think it's interesting to understand what caused the epoch of reionization, but also what are the consequences of reionization actually happening. And one lesson that theorists are learning using large computer simulations is that reionization actually prevented, after reionization, very low mass galaxies could not easily form anymore because the gas was heated and could not easily cool and therefore be bound gravitationally. And one consequence of that is that if reionization would not have happened, we would have seen the Milky Way would have had much more satellites, such as the Magellanic Clouds. Instead of 2, we would have had, well, we have more than 2, a few fainter ones, but we would have really orders of magnitude, 1 order or 2 orders of magnitude more faint satellite galaxies. So that's another, it's interesting to know why do we not have that.
So before we go to a few more questions on YouTube and to come back to CR7 and discuss it. So it was technically in December 2014 that we were able to measure the distance to CR7 and to confirm it at a redshift of approximately 7 with Keck. This happened on Christmas Eve, actually. It was quite spectacular because you could see the signature of Lyman alpha photons that we've already talked about after they have traveled throughout the universe, the expanding universe, for almost 13 billion years. And this is what you can see on the left is actually a raw 15-minute exposure by splitting the light in wavelengths. So for those of you that have been looking at the comet NEO-WISE, CR7 kind of looks like a comet when you look at the spectrum. But unlike the comet, CR7 is now about 30 billion light years away. Jorrit, do you remember when you got to see these data for the first time, and what was your reaction?
Yeah, I think I was at my wife's parents, and I saw it on a cell phone. I was very excited during Christmas dinner, and they were like, "What are you doing? What are you talking about?" So yeah, that was nice. But I particularly remember very well actually seeing the galaxy, the candidate galaxy at the time, because we didn't know the distance yet, but we had very good indications. I remember that very well because actually, unlike Heather, I spent a full year looking at near infrared images, looking for CR9s, or with basically no success at all. Like we spent hours at looking at hot pixels and any other detector artifacts and variable sources. So having a lot of experience in looking at objects that are not real, when we saw CR7, there was basically zero doubt that this was not real. So that was a very exciting moment. I mean, from that moment already on, it was very, very unlikely that this was not a real distant galaxy. That was confirmed a few weeks later. So the most excitement was really in this first discovery to me.
I mean, it was nice to confirm the distance, obviously, but it was quite robust already. And related to that, can you tell us a little bit more about how you found it originally in the data?
So, well, Sergio reduced these very large images that you can see in David's back or in David's screen. And of course we don't, so the actual image is much larger than what you can see here. Here you actually are seeing two flipped images. But what we do is we use the computer to identify all these blobs in the images automatically. And we're now switching between two images. One image is the narrowband filter that Sergio explained, which contains the Lyman alpha line. And the other image is the broadband filter that is basically the same, except it contains much more light. So it actually contains more noise, mostly for CR7. You can see all, except for the central object, you can see all the objects are more or less the same in these two images. But this central object, CR7, is very different in these two. And that is the kind of characteristic that we looked for with the computer. And once we found about 100 candidates, we looked at all of them individually by eye like this. And this was one of the first ones we actually looked at, because we started, of course, looking at the bright ones.
And I guess one important question is, why did we name it CR7 if we're not really that big football fans?
Oh, it's a funny story, I think. Well, this was your idea. So the long story is, so my email address is my first name @gmail.com, and I always get emails that are meant for other people with my first name. And there's one guy who's a bit rich, and I was joking that we should name the galaxy Yorit after that guy, and then maybe he would, I don't know, fund us in our search for the next large numbers of these objects. But then you came with the idea that it was much better to look for someone who was a bit more famous and a bit more wealthy and perhaps a bit more interested. And actually the abbreviation works very well. I think it's not, it doesn't come out of the blue. Cosmos is the field where it is, and redshift 6.6 is basically 7. So that works very well. I mean, the official name would probably be GA1046 plus 0118 or so, which is not very exciting for people, and people don't remember it. So if you give it a good name, people remember it as well, and that actually, I think, is nice.
And obviously, I mean, it's named Cosmos Redshift 7. It's not named Ronaldo, so it's associated with, but it's not named really after it. Now, one thing that's important is after we got it confirmed, you discover that somehow there was data on it from the Hubble Space Telescope sitting on the archive that no one has used. And this is what allowed us to see the image on the left. So on the left, we have real data for CR7, where the green are these Lyman alpha photons from the ground, and then the different parts or clumps that we named ABC very originally are components within the galaxy. So can you tell us a little bit of what's going on, and at least the picture we had when we discovered it?
Yeah, I mean, this was all quite funny. I mean, I remember that we were about to finish the paper describing the discovery of the galaxy, And at the same time, we had to apply for time on the Hubble Space Telescope. And you first have to check, of course, whether the data didn't exist. And well, really by chance, it was in the corner of another image. But yeah, what you're seeing is that there are 3 clumps. The thing on the bottom left is probably not associated to this galaxy, but these 3 clumps are very likely are. For A and B, we're 100% sure, and for C, it's quite sure. As sure as you can be, I guess. But what you're seeing is basically, so the scale is 5 kiloparsec. That's quite large. Our Milky Way is 20 kiloparsec, I think, in diameter. But for these, what you're basically seeing, and that's illustrated by the artist's impression, is that these A, B, and C are complexes of stars. They're groups of young stars. They're very blue, which means the stars are young and hot. Even though B and C may appear to be a bit redder, which indicated, so at the time we thought that could indicate that the stars in these clumps B and C are a bit older. And very hard to know that for sure, because we are only seeing the young stars. We only see UV light from young stars because we don't have the telescope yet to actually look at older stars, which you could use to confirm that picture. The most exciting thing is this green envelope of Lyman alpha light, which highlights the gas around these stars. That's really the gas, that's basically the gas from which these stars are forming. And we also saw indications of other line emission from helium-2, which is only excited by stars with effective temperatures of 100,000 Kelvin, which is 20 times hotter than our own sun. It's very hard. So these stars are very rare in galaxies like our own Milky Way. And those properties were predicted from very early generations of stars. So this was really the exciting thing about this galaxy. There are also other ways to explain all these different tracers of light. For example, including that the majority of light is actually powered by an accreting supermassive black hole instead of stellar light. Yeah, so this made this all very exciting in this 2015 paper.
So the other thing is, meanwhile, we got the chance to actually point this amazing telescope, ALMA, that really added to the puzzle, and I guess really show that the galaxy does contain at least some heavy elements, right?
Yes, exactly. Yes. ALMA was actually very new. It's a very new telescope. I think it's only available to international observers. It's actually one of the few telescopes from which people from across the world can actually use it. But at the time, this was a very new telescope, and it has the capabilities to observe in the sub-millimeter in microwave wavelengths, and in that wavelength regime, you can look for emission from the gas in galaxies, and in particular gas that is enriched with carbon. And we were actually not expecting to see it, because in all the other galaxies at the time, people tried a lot with ALMA, and no one actually saw carbon-2 at the time. This picture changed a lot during the recent years, and we actually also were one of the earliest to actually see carbon-2 in a galaxy like this. So an extremely young star-forming bursting system, which is likely very metal poor, and there's likely little dust, otherwise we wouldn't see the Lyman alpha photons. But we actually saw carbon as well throughout the system, indicating that it's basically on the scales on which our data smooths everything, because we don't have a very sharp picture, of course. There appears to be metal-enriched gas throughout the galaxy.
Now, also together with CR7, we actually discovered another galaxy, and it was named Masosa. So can you explain where the name comes from and why CR7 suddenly got really famous and Masosa is probably a galaxy no one has heard about?
Well, yeah, so, well, if I remember correctly, the story is that, so I told my girlfriend at the time, Rachel, about CR7, and there was another galaxy similar to CR7, which is named Himiko. And we wanted the name that sounded a bit similar to Himiko. I mean, just the kind of staccato it has. That was also a bit funny. So Masosa stands for Mateus, Sobral, and Santos, or with me, David, and Sergio. We were the first three authors of the paper. But actually, we're not the first ones to do this. There's also a Galaxy IOK1, which also refers to the first three authors of another paper. So this is actually not that uncommon. So this galaxy is also very bright, but unlike CR7, it's not. We did not see any other emission line, and that's why it's a bit has been less studied actually. But probably so CR7 is basically three galaxies together, and Masosa is probably one or possibly two, but it's a bit less extreme.
And of course, a big difference is Masosa was not on the Hubble archive, so we actually had to wait quite a lot and get our own data, which was quite cool. And I guess this is how data from Hubble looks directly when you download it, just so you have an idea. This is reality. And the Masosa galaxy is not the big, bright, beautiful thing. It's actually the thing that's highlighted by the green circle. Right? So this is how a very distant galaxy looks like, even with the Hubble Space Telescope. The thing next to it is relatively distant, but quite nearby galaxy. And the other thing with the spikes is a star in our own Milky Way. Jorrit, out of the galaxies that you've been involved with and studied, especially like the 5 super bright ones, do you have a favorite out of them?
Well, not really a personal favorite, but there is one that I think is most exciting, and that's actually a galaxy that we didn't discuss yet. And I think also in general, the community, well, it starts to be known a bit, but I think it's much more exciting. It's called COLA 1 and named Cosmos Lyman Alpha 1. And it was discovered by a team in Hawaii by Esther Hu and collaborators. And actually it was just outside of our images. So we couldn't have found it ourselves because we just didn't look at that part of the sky. But later during their paper and some geometry, we could actually find and confirm it as well. And the exciting thing is that this galaxy, it's a bit complicated. So the Lyman alpha line is typically one single asymmetric emission line, but in this galaxy we actually see two Lyman alpha lines, one on shorter wavelengths, and that's actually very hard to explain for galaxies early on at this point in cosmic time. And it indicates that this galaxy is much more extreme in terms of how many hot photons it produces, and it's like residing in a region of the universe that has been re-ionized relatively early on. And understanding this galaxy is much more, I think it's very interesting, and there are more open questions currently.
And Sergio, do you have a favorite out of these bright ones? Is it also COLA 1?
Well, I was going to say Masosa because, well, I think it's really cool having a galaxy with like a bit of your name. But yeah, well, but I also obviously really like CR7 because of the impact it had in the community and even, well, outside the scientific community, because there were a lot of outreach events and it showed up in a lot of mainstream media and even in things that had nothing to do with science, like sports websites and sports magazines, where it's because, well, Cosmos Redshift 7, CR7, also by coincidence shares the same initials as the football player. And it got people interested in, oh, CR7 now has a galaxy, and I think it was a really good, it ended up being a really good way to actually get science to people who would never have heard about things like this.
And Jorrit already said a little bit about his favorite step of discovering galaxies, but for you, Sergio, what was your favorite step? Was it the final thing? Was it reducing the data? Was it identifying it?
Well, I think I like the whole process, but maybe if I had to say a single step is when we basically have the first version of the candidates and we run our scripts, we give the parameters of the properties that we look for, a very strong emission in this band, not very strong emission on this band. And then we get a catalog with 100, 200, 300 galaxies. And then we can actually open them in the images and go one by one and actually look at them. And I think that's the coolest part, like actually looking at the first time for these galaxies, and maybe for the first time anyone actually looked at them.
And I guess along that process, some potential super bright distant galaxies ended up being something else. And Jorrit already alluded to it, but can you explain kind of the list of potential things that looked like distant galaxies, but actually were something else?
Yeah, so because, as I said, when we select galaxies, we look for specific properties, but sometimes that there are other objects that may have those specific properties by coincidence, by chance. And well, it can be, for the first thing is that when we look at Lyman alpha emission at some wavelength, it can also be a different line, such as H alpha or O2 at much lower redshift, which happens to be redshifted to that specific wavelength. Even though we apply steps to prevent that from happening, sometimes because it's thousands and thousands of sources, some have weird emission, weird shapes, and actually look like the very distant galaxies, even though they are not. And then the second one that Jorrit already mentioned is supernovae, because we look for sources that have very strong emission in the narrow filter, which usually means there's an emission line there. But what sometimes happens is that if we take all the narrowband observations during 1 week, it may happen that there was a supernova that went off in that week. And when we look at the narrow image, we will see a very, very strong emission, while there's nothing in the broad image, which we think, oh, there's a super booming emission line, but it's actually just a supernovae. And yeah, even though there's people who are the other way who think, oh, supernova is super interesting, I really want to study these. When you are looking for very distant galaxies, sometimes it's disappointing when it's a supernova. And I think, and the third one, which also happened, is near Earth objects. For the same reason as a supernova, is that when you take the narrow image, it may by chance have an asteroid or any other objects that happens to go by that region of the sky, and you look at it, and because there's a very strong emission there, well, emission is reflection from the sun, it's not from the actual asteroid, and we think, oh, there's actually a source there. And there was even one of them which we took multiple images of. So the way we take the images, we do multiple observations and then we stack them all together to remove noise. But there was one asteroid that was moving, and so when we stacked all the images, it looked like a very elongated emission, and it was super interesting. But then we went and checked the images one by one, and we could see the asteroid moving from frame to frame. But we take steps to prevent this from happening, like taking the narrowband images at different times of the year or a few months apart, which usually rules out most of these issues.
Now, Heather, in your current work, can you tell us a little bit more about it and about the survey you're trying to conduct in the Cosmos field? Which instrument are you using, for example?
So I'm using data from a survey called YNBS, the Wire Narrowband Survey. And this is something that David designed, like chose where to look in the sky and everything. And it's the data was collected with an instrument called Hawkeye on the Very Large Telescope. So yeah, this is near infrared data. So the narrow bands that I use is around 1016 nanometers. So yeah, we are going to pick up, so similar to what Sergio was saying, we won't just pick up the the Lyman alpha emitters will also pick up some other emission lines like hydrogen alpha and O2 and O3, but I'm also going to study those. So that's lots of interesting work to be doing as well.
And if you find any, do you have plans for any specific telescopes that you'd like to point to these galaxies?
Yes, so similar to what with CR7, what's been done with CR7, if we looked with ALMA or HST, that'd be really cool. Maybe someone else in the future, a future PhD student might look at them with JWST. That'd be really cool. See the cutting edge science that can provide us. That'd be really cool.
Yeah, and Jorrit, I guess an important question that we haven't really covered is, so thinking about CR7 and the artistic impression. So we're seeing it as it was almost 13 billion light years away, years away. So if we could actually have a way to make time run forward, how should this galaxy look like? Will it be anything like this or very different?
Well, it will look very, very different than the artist impression, because all the young stars, all the blue stars will die. They will likely explode as supernovae, and then black holes and neutron stars will remain. What will also very likely happen is that all these different clumps will merge together. There will be even more galaxies that currently are quite far away from this galaxy. It will also accrete. Exactly shown like this. And actually the CR7, even though it's observed roughly 600 million years after the Big Bang, it already has a similar mass as our Milky Way currently has, 13.6 billion years after the Big Bang. So that's it's forming much more rapidly, and it will likely also at some point the galaxy will be so massive that a supermassive black hole will form in this structure. The supermassive black hole will actually start to emit light, in particular because of the accretion disk around it, illustrated here. And eventually what will very likely become of CR7 is a large elliptical galaxy. For example, this is an elliptical galaxy. I mean, you hardly see a galaxy. It's basically a very diffuse, but very sharply concentrated blob of stars that are basically in random motion around each other instead of being rotationally supported. You can actually see a jet from the active galactic nucleus here. This is likely how CR7 will look today in its local rest frame, of course.
So CR7 will basically be very likely an elliptical galaxy, and very likely at the center of like a galaxy cluster, and it'll probably be very dead. So I guess that's what happens to very active galaxies. Before we talk a little bit more about your paths, and before we show people how they can find CR7 and other galaxies, I think we have a couple of questions from YouTube, starting from Louis about James Webb.
Yes, so Louis asks, why is the James Webb Space Telescope raising astronomers' hope? Is it likely to help us significantly improve our understanding of the universe?
So why should people be excited about James Webb, the telescope that is always 2 years away, or 4, depending on the year? Jorrit, do you wanna answer that one?
Sure. Yeah, of course. Yeah. I mean, yeah, we're waiting. I mean, the telescope was designed in the end 90s, so we're already waiting for this for a long time. But it's probably worth the wait, because it will be, in particular, so James Webb will be launched into space, and unlike Hubble, which orbits Earth, it will be sent to L2, which is the stable position where the Earth's and the Sun's atmosphere actually stabilize. The gravitational attraction stabilizes. It will have a very large solar shield, the size of a tennis court, and that will basically put the telescope in the shade, and it will allow very sensitive infrared observations. It will have a 6-meter mirror, which is almost 10 times larger than Spitzer, which you could see as the predecessor of James Webb Space Telescope. And in particular, so we need this infrared coverage, infrared sensitivity to look at very distant galaxies, because all the light of these galaxies that contains information about the stars and the gas is actually not observable in the visible wavelengths anymore. So the spectroscopy, which will really be, I think like 1,000 or even more times more sensitive to what we currently can do in the mid-infrared. So for this galaxy CR7, we will be able to measure numerous emission lines just in 5 minutes of exposure time. They'll be completely different. And we can also look for much fainter and more distant galaxies. So for the quest of finding really galaxies that have stars of the first generation, I think James Webb will be very useful and needed.
And do you have any bets for what James Webb might reveal within CR7? Just so it's recorded and we can come back in the future and see if you were right. Do you think it will reveal any pocket of population 3, any weird supermassive black hole, maybe even extra components beyond ALMA?
Yeah, I would. Well, the spatial resolution is, I think, 0.2 arc seconds. It's around 1 kiloparsec, if I correctly. So, I mean, there probably are POP3 stars within this galaxy. It's just that they are buried within POP2 later generations of stars. I mean, and the light that we see is like a combination of everything. And the question is really, is it possible to observationally distinguish the fraction of stars that is still from the first generation? And can we then learn something about their properties? This may be possible. I'm not sure. I mean, maybe our best bet is actually not looking at the center of the galaxy, but at the outskirts of a fainter satellite, some small pocket of young stars that we haven't been able to see yet because there's just a few of them. And James Webb may reveal that. And the other thing is indeed that there may be also, maybe there are lots of stars hidden by dust. It's quite unlikely because we know there's little dust, but there could be old stars present in this galaxy if there was no dust, and we couldn't have seen them with the current telescope because we're basically blind in the infrared.
And Sergio, do you have any bet for what we may find in CR7? I think you're muted.
Well, it's the same that I said on the Portuguese web broadcast, that I think that it will be a combination of multiple populations. That yes, there may be, and I think it will be some POP3 contribution in the bluer clump. But obviously, we know that there are also other populations, and it's not a single POP3 population.
So no supermassive black hole?
I don't think so.
You don't think so? Okay.
Well, I think it may be there. The question is, I mean, the black hole is probably there. The question is whether it dominates the light, and I'm not sure.
Eder, do you have any bets or guesses for what we might find?
I don't know. I haven't worked with CR7 quite like you guys have, but yeah, anything new is always exciting. Hopefully, like some new galaxies, and yeah, it's all exciting stuff.
Extra satellites, maybe.
Yeah.
That we can't see right now.
Yeah.
I think moving on to the final part of the show, and before we show people how to find galaxies and getting to know you all a little bit better, I think we have a question from YouTube from Amaya about your interests.
Yes, Amaya asks, what are all your non-Lyman alpha related favorite astronomical objects, and what astrophysics topic would you study if you couldn't study distant galaxies?
Don't say extrasolar planets, or say it, it's okay.
Well, yeah. So actually, when I started my undergrad, I actually had in mind extrasolar planets, and it was only when I saw David's project which was finding super distant galaxies, Lyman alpha emitters. Is that where I actually started looking for very distant galaxies, and that I found my passion. But yeah, so maybe if I hadn't seen that project, I would have gone the extra solar planet way.
And Heather?
I guess I did really enjoy my MPhys project, looking at galaxy clusters. So maybe something like that, more low redshift, local universe, what's going on in these big structures, maybe something like that.
So high redshift, but in the 60s, right? Yeah. You're right?
Well, yes, I would. I mean, there are probably remnants of population 3 stars or first generations in our own Milky Way. If very low mass stars formed, which can live very long. So I would try to find those kind of objects. They're probably very hard to find because it's also unclear whether they exist. And it's also unclear whether they actually remain unpolluted by other stars. But I think that's also a very exciting research field, to use our own Milky Way, to do archaeology in our own Milky Way, to figure out how it looked like in the distant past, instead of looking at other galaxies.
And actually with the telescope on your on the right, on the INT, where we built a filter to find Lyman alpha emitters, we're actually trying to do that. And actually we just got data last night, so maybe it's there.
Ooh, what am I doing here?
Yeah, you'd be looking at the data already. Yeah, making the discovery. Now, to get to know you a little bit better, one of the things that sometimes ask, and some people just never thought about it or they don't have it, but what is your favorite telescope?
So I actually have two different answers. So the first one is Subaru in Hawaii, because a lot of the data that I've used, well, most of the data that I've used is from that telescope. So a lot of the things I've done are all because of it. And the second one is the one behind Yorit, the Isaac Newton telescope, because it was the one where I actually went there and I've observed there. I think I have like 40 nights of observing time in that telescope. And well, it's a 2.5 meter telescope, but you actually get to control it with your own hand. Well, not with your own hands, you still use a computer, but it's the one where you actually get to move it and calibrate it and feel the cryogen, and where you actually get lots and lots of experience. And yeah.
Heather, is it the one on your back, or is it the telescope?
Lancaster's very own. No, I would say my favorite is the Hubble Space Telescope, because I think it's really cool that we can like get things into space and observe from there. It's provided so much science that it didn't even expect. I think it's been going for like 30 years or something, and it's had like recovery missions, and it's produced like I think over 10,000 scientific papers, like provided data for those papers. So I just think it's really cool, and like without it, we would be much further behind, I think.
And you're right.
So yeah, so I like the INT as well, but another one of my favorites is actually ALMA, because ALMA is actually the structure around it is very nice. There's a lot of help in using your data. So instead of just getting your data and then saying good luck with it, they actually help you a lot, which I think makes the telescope a big success, because it's, I mean, you can spend a lot of money building the telescope, but also you need then to use the data. And the other thing is, it's also it's really international. It's I mean, built by a combination of the US, the European Southern Observatory, Chile, and also East Asia. So I think that's also a very nice step. I mean, why would every country or even institute have his own telescope with private access? I mean, it makes much more sense to combine resources. and built this groundbreaking instrument.
So the other thing is, do you have like a favorite astronomer or someone that inspired you to go into astronomy, either a historical figure or someone alive? Heather, do you have like favorite astronomer?
Yeah, so I actually got into astro quite late. Like I was already at uni, and I initially wanted to do particle physics, but don't used to talk about that. So it was actually like the astro lecturers in the department that really inspired me. So like Isabel and John and David, who taught me in my undergrad, and like discussed their research and everything they do. So like in second year when we learned about how David discovered CR7, I was like, that's really cool. How cool would it be to be able to do that one day? And yeah, so I'd say it was more those rather than historical figures.
And Jorrit, I mean, the Netherlands is full, like literally full of, I don't know, amazing astronomers and famous names. It's ridiculous, I would say. Do you have a favorite astronomer out of all those big names?
Well, not really one favorite. I like Kaptein, who is the Institute in Groningen is named after him because he actually made a lot of discoveries and he started thinking about reinventing astronomy. At the time, I think if I remember correctly, people mostly did astrometry, so measuring positions of stars. And Kaptein came with the idea to do spectroscopy. And he came with the idea because he actually didn't have a telescope. So instead of worrying about how to perfectionize his measurements, he thought about what to do in the future. I think that's quite an inspiration. Also more personal, I had also very interesting lectures in my undergrads, particularly one on observational astronomy, the one on observational astronomy where a Dutch astronomer, Yuri van Leeuwen, told lots of cool stories about going to telescopes and mountain biking in Mexico, and the big one, I forgot how it's called, the 100-meter radio telescope. Anyway, that was very nice as well.
And Sergio?
Yeah. So it's the same answer from the Portuguese broadcast that my favorite astronomer is you, because well, I was an undergrad with like zero research experience, and like I didn't even have like the best grades. And like I saw your project, and you were like always super interested. And I think it's a message for all, everyone that works in academia, how important it is to actually work with students and believe in them and look at them and see them as actual researchers and not just students that are just doing their undergrad. And yeah, so even in Lancaster, you've been working with like, I think last year or 2 years ago, you had like 30 or 40 students that you were actually doing a research project with them, and they all wrote an actual scientific paper and made an actual scientific journal together. And I think that's the important part that there should be more of in academia. And that's what actually got me into studying galaxies. Because when I was in my undergrad, I still wasn't really sure where I was going to, and that's what really decided, made me go through what I've been doing.
I mean, for me, I think it's also the thing that keeps me going is being able to work with people that really appreciate it. So thank you for that. So one final thing that I usually ask people is whether they've always wanted to be an astronomer and kind of when that clicked. So I guess Heather, was it already during university then?
Yeah, so I initially wanted to do particle physics and like live in Switzerland, work at CERN. But yeah, no, then I realized that once particle physics gets more complicated, I'm not that interested after all. And that astro was actually what I did want to do. So yeah, I was probably like first year of uni that I realized that I really wanted to do astro. And then when I was younger, I wanted to be like a medical doctor, like a feel like many people have that thought at some point. So yeah.
And Sergio?
No, so I was always a bit undecided. I never really knew what I wanted to do, but I always liked astronomy. So basically, in the year before going to uni, I had to decide, and I thought, oh, I always liked astronomy, so I think I'll go with these, and it is what I decided, and I stuck with it, and I don't regret it. Yeah.
So Jorrit, how soon was it for you?
Well, I wanted to be an astronomer as a kid, but then, and I also read a lot of books when I was 14 years old, like in a local library. But then when I actually had to choose what to study, I didn't want to like specialize in one topic immediately. So during my bachelor, my undergrad, I did a liberal arts degree, where you do many different kind of things. I actually did courses in economics and philosophy and history. And then I actually did astronomy only actually very little until I started in Leiden, where I did much more astronomy. Oh yeah, so so actually I was a bit undecided as well, and then I did one astronomy course, and I thought, okay, this was it. Yeah, I should do this more.
Now, before we end the last episode, we can all try to find CR7 with the real discovery data we used, and then also try to find other distant galaxies. And you can use now or in the future, I don't know how many years, until humankind is still around, and this video is on the web. You can use the comments below or at any time to add essentially coordinates of the galaxies you discover, or to see whether the galaxy you're discovering, someone else already found it. So the first step will be to find CR7. So this is already a zoom in. This is how it will look like. But all you have to do is go to our website, that's xgal.uk. When you enter that, it will look like this. And you go to the tab on the top that says XGAL DIY for do it yourself, and then pick Galaxy Hunting. So you'll have all the instructions step by step, including kind of a background of what are you really looking for. And what you need is to click download on the images and instructions. And also you need to download this tool, that's DS9. And you have a download for any of these platforms. So once you have them, there will be two images for CR7, depending on the light that we're looking at. So there's one for the green light and blue, where CR7 will not be. And you will then open the image of red and infrared light, where CR7 will be. And the transition essentially corresponds to this redshift of around 7. And the best way to do it is if you follow these instructions and you blink between frames. This is what we were doing, but now this is a slightly larger image, still very small. But Heather, Jorrit, Sergio, do you want to explain essentially what people should be looking for in this image?
Well, so you basically have blue image and the red image, and you are looking for sources that are in the red image but not in the blue one. So in this case, it's the two images are blinking, and yeah. So on the left, I'm not sure which one is which, but there's one red and one blue. When you have them blink, you can actually spot one or more galaxies. CR7 is there, which is very bright in one of the image, but not on the other one. And maybe it's not too obvious now, but I think, yeah, I can already see it. I think in a few seconds it will show where it is. And so you basically have to identify one galaxy that's very bright in the red image. Yeah. And I think
so it is definitely not in the center in this one, but it's not that far off.
It's not that far from the center.
Yeah. And the point is, once you figure it out, and I will add the coordinates of the galaxy where to find it. And again, you have these instructions in this video, and also on our webpage, there's even more detailed instructions exactly how to load and where to click. What you can do is then apply your knowledge to find other galaxies. So it's exactly the same thing. There will be an image that's green and blue, just like for CR7, but it will be a larger image with many more of these distant galaxies. So they will be called Cosmos. It's still just a tiny little fraction of the full data, but it's much larger than that chunk. And the point is to do exactly the same thing. Now, Jorrit, can you already find this obvious one there?
Well, if I look at this image, I first think that I need to re-reduce because there's a slight position shift.
It's all Sergio's fault, I'm sure.
Yeah,
Just
probably.
kidding.
So the cursor is showing you two quite obvious, in this case, galaxies that satisfy this condition. They are very bright in the red and infrared, and that they disappear in the blue. And what you'll be wanting to look at is for those values of alpha and delta. Those are the coordinates of the galaxy on the sky that will show up when you have your cursor somewhere in the image. So the coordinates in Cosmos will be something like 10 degrees. So when the mouse now moves to that super obvious one that you can see, the coordinates are something like 10, 0, 1, 0, 0, 0, 3. So those are the kind of things you can write in the comments, or you can check them out. Eder, what is your record on this image? How many have you found?
Well, I am famously bad at spotting any of these. I don't know, I just can't work it out. But I've done it with visitors on outreach talks and stuff. And I think we've managed to find, I think there might be like 10 or even more. I'm not really sure. But I can't find any of them. So
it's a good thing we have computers to do that for us. So it doesn't rely on our visual capacity. I think the record has been 12 by something like a 12-year-old. I guess young people are quite good at doing this, apparently. Sergio, do you have a record for this?
I have no idea. Yeah, so but that one is just an example. It's not an actual real one. But I think I found, maybe close to 10. Yeah, that one is quite clear.
Yeah, so this one is real. The other one, and actually there's two extra ones when you zoom out in the image. They are incredibly, incredibly bright. I mean, way brighter than CR7. And the reason for it is because they're fake. They've been implanted so you can kind of calibrate and understand what you're looking for. So those I actually took from some other images and I've placed them in different places. So you should at least find 3. That's like the bare minimum. And then if you make it to 10, you should probably send us an email and start working with us. And if you get more than 10, then you probably get hired immediately. Do you have any extra final thing you might want to say for people watching at home about this research field?
For me?
Any of you? Jorrit, do you want to say something?
Stay tuned. I need to think deeper.
Think deeper. Okay, that's fine. That's a good answer as well. So assuming that you're all done and that people at home now know how to find CR7 out of the galaxies, we hope you can explore that and also show your parents or children or students, whatever. And that's essentially all we have time for today. So thank you again. Thank you so much, Jorrit.
Wait.
What's happening?
You didn't answer 1 or 2 questions for you, David.
Oh, but they're for me, so.
Yes.
Yes, you actually started. that this is the last episode, so people can ask you questions as well.
Go ahead.
So one of the questions is, what would you say is the most exciting, lesser known paper you've written or co-authored, and why?
It's a complicated, tricky question. It's probably a paper I wrote when I was still a PhD student, where I've implemented a lot of kind of, different and new methods. And I was trying to study how galaxies cluster together on the sky, and also what that means for the dark matter halos that they reside in. So for some reason, because it was done with these narrowband surveys, and no one else did it before, it wasn't that well cited or known, but it has really cool results about how galaxies may or may not evolve, star forming ones. So I would probably say that's the one.
Nice, cool. And I think also Yarit had a thing to ask also about maybe why you became an astronomer.
Yes, you dodged that question.
Did I?
Or maybe-
Okay, why I became an astronomer. I guess, yeah, so before going to university, I didn't want to do particle physics. I wanted to do literature, Portuguese and English. I was very specific. So that was my second choice as I applied. And physics with astronomy only became my first choice because I got to participate in a kind of a contest for high school kids about astronomy and space. So I gave a presentation about black holes. That was really cool. And I got to be in the Lisbon's observatory for the first time. And I gave the talk inside, and it's an amazing building. So I think that's the thing that really shifted me towards astronomy, was also being heard by astronomers and actually taking you seriously. It was actually like a 1 hour lecture almost for a 17-year-old that I guess it's quite scary, but I didn't think about it at the time.
Thank you.
Yeah. So I think now it will be the end. So I'll thank you again, Yarit, Sergio, Eder.
Yeah, thank you.
It was really brilliant to have you for this season finale. And it's been a true privilege to work with you so far. And I'm really looking forward to what the future will bring. So let's have a big round of applause for you all. Also, thanks to everyone who watched, participated, and asked questions during these 8 episodes of the English and version during essentially June and July. And for that, I would also ask for another applause, and also to thank the voice from beyond that's been reading all the questions. So far, apparently we've had more than 1,000 people watching our shows, and our videos have had more than 10,000 views and have been watched for a total of 1,200 hours during the last 2 months. So thank you all for watching. It was really brilliant to share astronomy, science, and other stuff with so many people, along with revealing the human and diverse side of looking up. We got to know for the first time, or even better at times, astronomers and scientists that, regardless of their beliefs, age, sexual orientation, color, or nationality, have been inspired to look up and inspire others to look up and beyond themselves. People that are constantly facing our humongous cosmic insignificance and remain humble, but without losing sight of our ambition to always know more and share it with everyone and everywhere. In the words of a Portuguese poet, we are nothing, but we have in us all the dreams in the world. So let's keep dreaming. In case you missed an episode or you only saw this one, feel free to check all of them out in our YouTube channel. We have talked about the gas giants, the dark side of the universe, galaxies, super distant galaxies, galaxy clusters, supermassive black holes, galactic archaeology, globular clusters, and also in the season finale, the discovery of CR7 and other super bright galaxies. Don't forget that you can subscribe to our YouTube channel. You can also check the full program and past episodes at xgal.uk, along, as we've showed, trying out and sharing our do-it-yourself, DIY, activities with real astronomy data and detailed instructions. So you can find distant galaxies, you can map the universe in 3D with SC4K, the survey that Sergio has been working on, or you can become Vera Rubin and discover evidence of dark matter and galaxies. And this means you can do it with your computers and at home. So this is really the end of
The Earth is flat on planet Pluto.
And I would finish by saying that we should all keep looking up and see you at some point in some other formats. Bye, everyone.
Liftoff of mission 41D, the first flight of the orbiter Discovery, and the shuttle has cleared the tower.
Welcome home, Columbia. Beautiful, beautiful.
So I have to take it up to hangar, Joe?
We're going to dust it off first.
3, 2, 1, 0, and liftoff! Liftoff. Americans return to space as Discovery clears the tower.
Roger roll, Atlantis.
Houston now controlling the flight of Atlantis. The space shuttle spreads its wings one final time for the start of a sentimental journey into history.